Okay, students. So I just want to make a little run through of the kinetics associated with the interactions between ions, for example. Right? Most times we refer to this as what we call the kinetic salt effect, or kinetic salt effect, rather. All right. So I just want to go through how we can formulate basically rate expression or general expression that could allow us to determine some important features of such reactions. So let's say, for example, we have a ion A, right, of charge ZA reacting with another ion B of charge ZB, right? And you can imagine that there's some sort of equilibrium where they pair, right? This is like the ion pairing equilibrium. AB, right? Both of the ions coming together. And of course, you can imagine that the charge on this complex would be ZA plus ZB, okay? And then this complex could break down to give you your product P, governed by a rate constant. Let's call this K2. This equilibrium, we could call it KIP, right? Equilibrium of ion pairing. Now, one could imagine that the rate, right, the rate of formation of the product is equal to K2, right, times the concentration of the complex AB. Okay, one could imagine that that is the case. But of course, we have to give also some consideration to the ion pairing equilibrium, because of course, when the complex is formed, that complex could break down to give you back the individual ions. And so what we could do is to give a little bit of consideration to that by rewriting this expression in a more interesting fashion. For example, K2 times, right, uh, A, B concentration, right, over concentration of A times the concentration of B. And this is basically the equilibrium expression. So I put EQ there, EQ, yes, times concentration of A times the concentration of B. And this makes the equality here true, because if you think about it, these basically cancel. So what you find is that this part of the expression comes back down to be all of this. Okay? Yes, it comes back down to be all of that. All right, good. Now, let me just remove that, the green, to reduce a little bit of the uh, confusion here. All right, so what we could do, we could actually group these two and just give it a name, K. And so what you find also is that the rate of the process could be K times AB. Okay? Now, let's move forward. This part here is an expression for the ion pairing equilibrium. Okay? And so the rate comes down to be, rate is equal to K2, right, times KIP. Now, I'm going to write also the equilibrium expression for the ion pairing, but I will consider the activity coefficient, that is. A matter of fact, let me not use X, let me be more specific instead of saying X. And you'll realize that I am writing the ratio of the activity coefficients in an inverted fashion. Instead of writing product over reactants, I'm writing reactants over products. Why is that? Well, that is because the equilibrium constant for ion pairing, I have summarized it. Instead of writing this expression, I have summarized it. And so what you have is a situation where the equilibrium constant for uh, ion pairing is multiplying the numerator alone. Okay, so it's basically going to end up, it will end up in the numerator, which will be problematic, all right, mathematically. So if I need it to be mathematically correct, instead of writing product over reactants, I have to do reactant over product. Okay, right. So if we should write KIP as the expression, then this expression will end up in the numerator and mathematically would be incorrect. We cannot have that. Okay? All right. Let me just remove some of the confusion from here. Okay. All right. Let us move forward. Okay. This is our expression that we arrived at. Now, this part is for when you're dealing with, this is like a ideal situation where you're dealing with dilute ions. This is basically rate constant for a very dilute solution. Sorry, not dilute ions, but a dilute solution, right? Or what we call infinite dilution. That's where the solution is so dilute that you just have a few ions running around. Okay, this part of the expression was very necessary because we needed that to account for interactions between the few ions which are present. So that's what the activity coefficient is responsible for, accounting for the interactions between ions. Okay? All right, let's move forward a little bit with this expression. Let me just clear this and we can move forward. So we said that the rate works out to be K2 times KIP, equilibrium constant of ion pairing, right? Activity coefficient of ion A, activity coefficient of ion B over the activity coefficient of AB, which is the complex. All right, now what we want to do is to invoke the limited Debye-Huckel theory, which says that Y of an ion X, right, the activity coefficient of an ion X is equal to minus 0.0, well, not 0.0, but 0.509. Let me just fix that quickly. Here we go. 0.509, okay, times the charge of the ion, and the ion is called X, and we square that, times now the square root of the ionic strength. Now, this expression allows you to calculate the activity coefficient for a single ion. Okay? Now, we need to apply it here. Okay. And there should be one more thing. Let's see. Let's make sure. And this is the log. Okay? Limiting Debye-Huckel theory, which works best for solutions which are dilute. That is less than 0.01 molar. Okay, now let's see how we can fit our expression that we derived for the ions A and B reacting to give you a product P. Now we are going to fit all of this. Well, this part we already explained that this can be referred to as K naught. Okay. Now the other part that we have a problem with is this. We need to fit this into this expression. Now remember that the log of a product, right, is basically the same as the sum. So if I'm going to take the log of this thing, right, I will have, let me just change the color a little bit. I will have log, okay. Let me just go over a little bit to give us some space. I think I might run out of space. All right. I'm going to substitute it in everything. So I'm going to end up with now log y a, okay, is equal to minus 0.509 z, this is a 9 by the way, z, I'm going to put za squared root I plus, alright, plus this other expression now, which would be 0.509 zb squared root I. And you're going to see how all of this makes sense. Matter of fact, I could, okay, minus now, which is the one because of this one, you know, in log, ratio is the same thing as difference. 0.0509 z AB, right? Which would be basically ZA plus ZB squared root I. Okay? Now, no matter of fact, let me remove this part from here such that you don't get confused. Okay? And let's just explain. Why is it that I have a plus sign here? Why is it that I have a minus sign here? Well, I have a plus sign over here because there's the activity coefficient of A and B are being multiplied at the top. In log, multiplication is the same thing as sum. Where did the log come from? Here it is. All right. So this expression right here is actually the log, right, of activity of ion A, whereas this one over here, right, is really the log of the activity of ion B. This one down here is actually the log of the activity coefficient of the ion pair AB. Okay, let me remove a little bit of the confusion here. All right, why is it that there's a minus sign here? In log, ratio, which is division, is the same thing as difference, subtraction. That's why I have that. Okay, all right. Okay, now what is interesting is that there are some things which are common, which we can group. This part is common. This part here is also common. See? Common. So what we could do then, alright? What we could do is to write, and this R should really be written as a rate constant. Moving forward, right? We're going to summarize. This is what we'll do. K is equal to K naught plus. Okay? Now let's summarize. Let us summarize. Okay? Now let's go. This number here is common. Alright? And so what we'll write is minus 0.509, right? Because that won't change. Root I won't change. It's common for all of them. Okay? And then we could write over here ZA, and then what else we have? We have also ZB. Okay? We have also ZB. So we'll put plus ZB And then over this part now, we have also this minus sign, this one. So it would be ZA, ZB, right? All squared. Okay? And we know what happens with that. It comes down to be, let's say, ZA squared, okay, plus 2ZA ZB plus ZB squared. Okay? Yes. There's a minus sign outside. And we have ZA outside plus ZB. Alright, and I'm just going to put in the rest of the expression so we don't get confused. 0.509 plus K naught. Okay? Now in the end, we end up with ZA plus ZB. This minus sign outside will cause this one to be, of course, don't forget that these were squared from up top, right? Remember, they were squared. Let us almost got into trouble there. Okay. Minus now ZA squared plus 2ZB ZA. Now if you could write ZB for ZA first and ZB, no problem, it's commutative. ZB squared. Now look at this. Don't forget the signs. Don't forget to deal with the signs properly. Okay? Or else you'll get into trouble. You'll get it incorrect. Now this minus sign will go in front of that one. It will also go in front of that one. And the same over there. So we end up with minus there, minus there. Okay? Yes. Okay? Alright. Let's tidy things up a little bit. Alright, let me just create a little bit of space up top. I don't want to remove everything because then we'll just get lost and don't know where we were. So let me just erase slowly. Okay, let's see. So let's put it back here. K is equal to K naught plus minus 0.0509 root I, and what we have behind there is ZA squared plus ZB squared, right? And then we have also minus ZA squared minus 2 times ZA ZB, right? It doesn't matter. You could put ZB in, right here. You could put ZB first or ZA. It doesn't matter. It's commutative, right? Minus now ZB squared. As you can see, right? Now let me use another color ink. This one we cancel with that one. All right. And then let's try another color. This one can cancel with that one. Okay. So this is what you'll end up with. And let me just clear up what I have down here to avoid any form of confusion. Okay, so here we go. So we end up with K is equal to K naught, yes, plus minus 0.0592, not 592, but 509, sorry. Thinking about electrochemistry. Minus 0.509, okay? Root I, and all that you have left over there is just times minus 2 ZA ZB. This 2 could multiply that one. All right, and because it's two negative signs, then they will clash. You get a positive, so you end up with something like 1.018 root I, okay, ZA ZB plus K naught, yes, is equal to K, okay, yes. Now, this might look a little bit strange because when we were working the entire thing out, there was a log, this log. And what we should have done basically was to take the log of this. So this should have been logged all along. Okay? Yes, you should have had a log there. Now, because if you look at this, the starting point required a log, right? Required you to log. So you have to pay attention as we get into trouble. Let me just adjust this a little bit. Um, log k is equal to this one, and so we log k, this is k naught, yes, is equal to log k naught. Now you could take this and put it at the front here if you want. It doesn't make a difference. Same thing, right? Uh, right. So you could use this expression as is, or you could rearrange it a little bit and say log k minus log k naught, which is the same thing. That is, it's equivalent to saying log k over log k naught, okay? Which is the same as writing log k over k naught, right, is equal to 1.018, right? ZA ZB root I, right? Now in terms of the application, of this expression, okay, let's see how we can apply this. Now what it means. I write both expressions. I write the one that says log k over k naught, right, is equal to 1.018 ZA ZB root I. And I'll also write the other one. The other one says, right, log k is equal to log k naught plus 1.018 ZA ZB root I. Alright, what's the difference? What can we do with them? Now, what you could do, let's look at this one over here first. If you do a plot of uh, log k over k naught versus root I, okay? Let's say you do such a plot. You should get a line that goes through 0. The line could be going like that, or it could be going like that. Let's look at the scenario. Let's look at this case first. Let's look at this case up here first. What is it saying? The fact that the line is positive. Well, first of all, let me put another color so I don't confuse it too much. This is y. This should be your x. This is your slope, m, and there's no intercept. It goes through 0. Okay. The only way for your line to be positive like this is if both ZA and ZB are positive numbers. Well, 1.018 is already positive. So the only way for you to get a positive slope is if both ZA and ZB are positive. That is, if you're dealing with the interaction of two positive ions. Okay? Is there another way for it to be positive? That is the question. because I just said, well, the only way you get to be positive is that. Now, look at what is going on here. You're dealing with a product. Look at it. Think about it. Which other way could you have, or could you get a positive line, or a positive slope, if you want to look at it like that? The only other possibility is this. All right, even though I said there's only one, but look, there's another one. Let's say, let's say A is positive, right? So if these two are like that, A, or let's say both of them are negative, then would this work? I think so, because the product of two negative numbers will give you a positive number, right? So if you're dealing with two, the ions must be of the same charge. The ions must be of the same charge then for you to get a positive slope. If you get a negative slope, then what can we say? Well, because we know what will give us a positive slope, then we can figure out what will give you a negative slope. It must be that if one ion is positive, the next one is negative. Yes. If both of them are negative, you won't get a negative slope because the product of two negatives give you a positive. Two negatives give you a positive when you're multiplying. So it must be a negative and a positive that will give you a negative slope. Okay? All right. Now, from this plot, you won't be able to figure out K naught. Okay? You won't be able to figure out K naught. However, if you use this one, you could figure out K naught. Because when you do this plot, right, and the reasoning with regards to positive slope or negative slope will be the same, but it's just that in this case, now you'll have an intercept. And this intercept is equal to log K naught. Because now what you have is a situation where this part here is C, this part here is M, and this part here is X. Of course, this is your Y. Do you see? Yes. So when you take this number, you have to take the antilog of it, sorry, to get the K, which is the rate constant at infinite dilution. Okay? Great. All right, guys. I hope I was not too confusing, and that you would have gotten something or some sort of enlightenment from what you know I just discussed. All right. You have a good day.